Hello everyone, this is Thermochemistry Made Simple with Ms. Rodriguez, and today we're going over everything you need to know about the Thermochemistry Unit in high school chemistry. So today we're going over types of energy, endothermic versus exothermic, specific heat, heating curves, and calorimetry. But what is energy? Energy is the ability to do work. Chemical reactions either require energy or create energy. There are different types of energy. So first we have kinetic versus potential energy. Kinetic energy is the energy of motion, while potential energy is stored energy. So in this example, when the ball is at the top of the hill, it's all potential energy. On its way down the hill, the potential is converted into kinetic, and by the time it gets all the way down to the bottom, it's all kinetic energy. Chemical energy is potential energy of compounds that can be released in chemical reactions, while thermal energy is the energy of an object due to the random motion of its particles. Thermochemistry are the changes of heat content and heat transfer. It follows the law of conservation of energy, also known as the first law of thermodynamics. This states that energy cannot be created or destroyed, only transferred. So one type of energy may transform into another type of energy in the course of a chemical reaction. Heat is always going to move from high to low, never in reverse. That means if you have an object that's hotter and an object that's colder, the reason why one of the objects feels colder is because it is lacking heat, not because it has cold energy, if that makes sense. So the heat is going from the hotter object to the colder object and never in reverse. Heat is not the same thing as temperature, even though in everyday life we use the two words interchangeably. Heat is the energy transferred due to a temperature difference. Temperature is the measurement of heat energy, and this can be measured using thermometers. Absolute zero is the lowest temperature that is theoretically possible. At absolute zero, particles stop moving. So remember, the faster the particles are moving, the hotter it feels. The slower the particles are moving, the colder it feels. As you approach absolute zero, the particles start moving slower and slower and slower, and at absolute zero, they stop moving completely. Now, this is theoretical. That means we haven't actually observed what particles do at absolute zero yet, but we have gotten very, very close. In order to talk about heat transfer properly, we need to know the difference between systems and surroundings. The system is the object in question, so whatever object you're talking about. The surroundings is everything else outside of the system. Thermal equilibrium is when both the system and the surroundings have the same temperature. And once they have the same temperature, then there's no more need to transfer heat. When temperature is not equal, then you get an endothermic or exothermic reaction. Endothermic is when heat is absorbed by the system, while exothermic is when heat is released to the surrounding. Heat is absorbed whenever we form chemical bonds, and heat is released whenever we break chemical bonds. When the substance absorbs heat, that means you have a positive Q, and we'll talk about Q in a second. When the substance releases heat, then you have a negative Q. An example of something that is endothermic is ice. So ice absorbs heat from the system. Remember, it's not releasing cold, it's absorbing heat because it lacks heat. An example of exothermic would be a fire. So fire releases heat to the surroundings. These are the potential energy diagrams of endothermic versus exothermic. Notice that in both diagrams, there is an activation energy. So activation energy is the energy used in bond breaking. So remember, breaking bonds requires energy. When energy is absorbed overall in the reaction, you have an endothermic reaction. That means that in the chemical equation, the energy or the heat will go on the reactant side of the reaction. While in exothermic, energy is going to be released overall in the reaction. So the energy or the heat is going to be on the product side of the reaction. Also note that in an endothermic reaction, the products have more energy, while in an exothermic reaction, the reactants have more energy. There is a formula for specific heat, and it is Q equals mc delta T. Q stands for heat or energy, and it's measured in joules. C stands for specific heat, and each material is going to have its own specific heat. M stands for mass in grams, and delta T stands for change in temperature, and it's going to be in Celsius. So what can Q tell us? When Q is positive, that means that the substance absorbed heat overall, so it's endothermic. If it's a negative Q, then the substance released heat overall, so it's exothermic. So like I said, each item has its own specific heat. The only ones that you really have to know because you use them so often is the specific heat of water. Depending on its state, the specific heat of H2O is going to change. When it's ice, the specific heat is 2.01. When it's liquid, it's 4.18. And when it's gaseous, it's 2.01 again. So here we have our example. A 15.75 gram piece of iron absorbs 1086.75 joules of energy, and its temperature changes from 25 degrees Celsius to 175 degrees Celsius. Calculate the specific heat capacity of iron. So we have our formula. We read the problem. We identify what we know from the problem. Notice that for delta T, you have to subtract. So delta T is a change in temperature. So you have to subtract your two temperatures, and we get delta T equals 150 degrees Celsius. We plug the numbers that we know into our formula. So Q equals mc, we don't know c, so there's our x, times delta T, so times 150. We solve for our c, that means the 15.75 and the 150 have to move, and how we move them is by dividing. So what we plug into our calculator is 1086.75 divided by 15.75 divided by 150, and you get your final answer, which is 0.46 joules per gram degree Celsius, which is the specific heat for the iron. Here's a slightly more complicated example. To what temperature will a 50-gram piece of glass raise if it absorbs 5,275 joules of heat and its specific heat capacity is 0.5? The initial temperature of the glass is 20 degrees Celsius. So again, we use the same formula. We identify what we know from the problem. Notice that in this case, we know Q, we know M, we know C, and we know one of the T's. So we know our T initial, but we don't know our T final. So that's what we have to figure out. We plug our numbers into our formula. So Q equals MC. Notice that for delta T, we plug in T minus 20. If you're more comfortable using x, you can put x minus 20 as well. Now we solve for our missing variables, so let's solve for t. So first you have to multiply. So 50 times 0.5 gives us 25. And you distribute that 25 to both the t and to the 20. So 25 times t gives us 25t. 25 times 20 gives us 500. Notice that it's a minus 20, so you're going to get minus 500. Now everything except for the t needs to be moved to the other side of the equation. So how we move the 500, the opposite of subtract is to add, and how we move the 25, so the opposite of multiply is to divide, so divided by 25. What we plug into our calculator is 5,275 plus 500 divided by 25 gives us a T final of 231 degrees Celsius. Now here's a practice problem that I want you to try on your own. So do exactly what we did in the last two slides. Identify what you know from the problem, plug it into your equation, solve for the variable that you're missing. So solve for your x. The answer you should get should be 13,794. See if you can get it correct, and if you can't, let me know in the comments, and I'll see if I can help you out. Now this is a heating curve, and this specifically is the heating curve of water. So water goes from solid to liquid at 0 degrees Celsius, and it goes from liquid to gas at 100 degrees Celsius. Other liquids are going to have other temperatures for their heating curve, but in general, it's going to look very similar to this. When you go from solid to liquid, you go through the heat of fusion. For water, the heat of fusion is 333 joules per gram. When you go from liquid to gas, you go through the heat of vaporization. For water, the heat of vaporization is 2,230 joules per gram. And there's multiple different ways to ask a heating curve question. So let's do some simple practice problems that have to do with our heat of fusion and heat of vaporization. How much energy is required to melt 50 grams of ice into liquid water? We use the formula Q equals M delta H. In this case, we're talking about fusion, so times heat of fusion. Notice that there's no changes in temperature mentioned in the problem, only that we have 50 grams of ice and it's going from ice to water. So that means it's at 0 degrees Celsius, so heat of fusion. All you have to do is multiply the grams. So we have 50 grams times our heat of fusion, so times 333, and we get the amount of energy needed, which is 16,650 joules. For our second practice problem, we have 50 grams of water and we're turning it into steam. So now we're at 100 degrees Celsius, so very similar formula, Q equals M times delta H, but this time instead of fusion, we're using heat of vaporization. So Q equals 50 grams times our heat of vaporization, so times 2,230, and we get the amount of energy required, which is 111,500 joules. So now we have a heating curve problem that does have temperatures. So we have 10 grams of ice at negative 20 degrees Celsius, which we're trying to turn into steam at 120 degrees Celsius. So how much energy is required? Notice that every time the line shifts, that's another formula that we have to use. It's a 5-step process because there are 5 different line segments that we have to do a formula for. For all of the line segments, we're still using the exact same formula, so Q equals MC delta T. And let's go ahead and take it one step at a time. So in the first section, we're going from negative 20 degrees Celsius to 0 degrees Celsius. Q equals MC delta T, so our M is 10 grams. Our C, because we're at ice, so C of ice is 2.01. Times our change in temperature, so we're going from negative 20 to 0, so the change in temperature is 20 degrees Celsius. We multiply our numbers and we get 402 joules. Now we're in our second segment, which is the 0 degrees Celsius heat of fusion. It's still 10 grams, but now we're going to multiply it by that heat of fusion, so times 333, and we get 3,330 joules. Now we're in our third segment, so we have to go from 0 degrees Celsius to 100 degrees Celsius. It's still the same 10 grams for mass, but now we're at liquid water, so the C of water is 4.18 times the change in temperature, so we're going from 0 to 100, so the change would be 100 degrees Celsius. We multiply and we get our answer, which is 4,180 joules. Now we're in the fourth section. So the fourth section is going through the heat of vaporization, but it's still the same 10 grams. So 10 times heat of vaporization, which is 2,230, and we get our answer, which is 22,300 joules. And now we're in our final fifth section, still the same 10 grams, but now we're at steam, and the C of steam is 2.01 times our change in temperature. So we're going from 100 to 120. So that's a change of temperature of 20. Multiply and we get our answer, which is 402 joules. Add all of your joules for each of the segments and we get our Q total, which is 30,614 joules. Now I know that this is a lot of steps. Most of the time you won't have to do this many steps. It only requires 5 steps when you're going from ice to steam or from steam to ice. If you're only going from ice to water, for example, then it would only be 3 steps. The last type of thermochemistry problem you could be asked is a calorimetry problem. Calorimetry is the process of measuring the amount of heat released or absorbed during a chemical reaction. For calorimetry, so in order to figure out the calories of something, we do have some conversion factors that we need, and that is 1 calorie equals 4.18 joules of energy. 1,000 calories equals 1 kilocalorie. A kilocalorie is also known as capital C calorie, and those are the calories that we see on the back of food labels. For our calorimetry example, if 20 grams of water at 30 degrees Celsius are mixed with 200 grams of silver at 350 degrees Celsius, find the final temperature of the system. The specific heat of silver is 0.235. So for calorimetry, you're trying to find the final temperature. That's always going to be the goal. On one side, we have the water. On the other side, we have the silver. Basically, for calorimetry, you're trying to figure out the final temperature by setting the Q's equal to each other. So Q equals negative Q. That means that one side of your equation is always going to be negative. So notice that on the left side, we have water, which is the positive side, and on the right side, we have silver, which is our negative side. But the formula is still the same for the Q. So formula is mc delta T equals negative mc delta T. On the left side, we're going to plug in all of the information we know about water. So M of water is 20 grams, C of water is 4.18. We don't know the final temperature of the system, but we know that the water started at 30 degrees Celsius, so minus 30, equals, now we're on the right side, so negative M of silver, so negative 200, times the C of silver, which is 0.235, times delta T. So again, we don't know the final temperature, so there's our X, minus 350 because the silver started at 350 degrees Celsius. To solve for our T, first we have to multiply. So 20 times 4.18 gives us 83.6. Negative 200 times 0.235 gives us negative 45. We have to distribute on both sides of the equation. So 83.6 times T gives us 83.6 T. 83.6 times negative 30 gives us negative 2,508. On the other side of the equation, negative 47 times T gives you negative 47 T. Negative 47 times negative 350 gives us positive 16,450. We have to get the T's by itself, so we're going to combine like terms. We do this by adding and subtracting. We can move the 2,508 to the other side by adding it. So 2,508 plus 16,450 is going to give you 18,958. We're going to move the negative 47t to the other side by adding. So 47t plus 83.6t gives you 130.6t. We get the t by itself by moving the 130.6 by dividing. So 18,958 divided by 130.6 gives us our T final. So the final temperature for the system is equal to 145.16 degrees Celsius. All right, that is everything you need to know for the thermochemistry unit in high school chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. Make sure to hit that like button if you found this video helpful, and subscribe so you don't miss any of my future chemistry content. I will be releasing more videos soon with more examples from thermochemistry if you would like more step-by-step examples. If you're a chemistry teacher and you would like access to this exact PowerPoint, it is on my TPT store called Chemistry Made Simple, as well as worksheets, labs, and activities that align with this unit and all other units of high school chemistry. I hope you have a great day. Bye!